All right. Well, if everybody's good, we'll go on and start.
We're good.
Good afternoon. We are Trashy, the autonomous trash collector. I am Michael Newman, the team lead for the ECE electrical engineering team. I also work with navigation. We also have Easton Van Every working on power distribution motors, Dustin Weathers working with power supply and distribution. Then we have Qua Pham working on software and navigation, and Randy Townsend working on sensors and navigation.
And so for the mechanical team, we are five mechanical engineer students. I am Mimis Khalil, the ME lead and responsible of CAD design. Bin and Swipper supports, we have Elise Belabidia, who is a mechanical engineer working on chassis and FEA material selection. Asma Shakir with CAD design again and responsible of Bin and Swipper subparts. And finally, we have Alinate Sliman and Wusaf Bili, who are working both on the track and wheels subsystems.
For the interface design team, we have Jeremiah Brooks, Alex Herring, and myself, Amber McDonald. We will be designing the interface to be used on both mobile and desktop web browsers.
And the team advisor on this project is Dr. Brian Jones, an associate professor here at MSU. He has a PhD in electrical engineering with a focus or a knowledge of robotics. General outline of today, we're going to start with the problem solution, go into our design constraints we decided on, the approach that fulfills the solution and solves the problem and within the constraints, and then we'll go into our current progress and conclude and answer any questions you may have.
So the problem that our team is facing here is not necessarily trash, but it is the collection of trash. And that process can be nasty and lengthy and costly at sometimes. And so to avoid the downsides to this process, our solution is an autonomous trash collector. So our design is able to be deployed in a specified area, and it is able to navigate that area and collect trash while navigating. It's good for, it's a lightweight and compact build, and it is very, very efficient process to use to collect trash.
From the start of our project, we have faced so many technical constraints. The first one concerns tracking system. Trashy can provide updated locations and also follow set route plans. The second to the weight. After some calculations, the maximum weight that can be reached while still being able to be lifted by one person is 22.68 kilograms. Our constraint number 3 has to do with the bin capacity, which is based on two criteria. The robot should not exceed 22.68 kilograms, and the fact that multiple robots will be working at the same time, so 10 liters capacity is the adequate choice. Application is our fourth constraint. ECE team has created an app that will allow customers to interact with Trashy in a very simple and stable way. The fifth constraint is that the internal temperature is monitored by Trashy so that any overheating is avoided. Now into our sixth and last constraint, which is the size of items that can be picked up by Trashy, and that any item whose size range between 2 to 10 centimeters for each and every parameter.
That brings us to our practical constraints. We decided as a team that the number one goal is safety, no matter what that we do with Trashy. That pertains to animal and human safety. The good thing about Trashy is it is emission-free because it is made up of all electrical components. We had to be cautious of the environment we place Trashy in. We want to be able to withstand dust and random rain showers, especially being in the south, as well as humidity. We want to do minimal maintenance as we can. The only maintenance we want to do is to either do a battery swap or a recharge. And as stated before, our end goal is to have multiple units working together. So we need to keep the functionality in mind as well. And we want to keep the cost down to a minimum as we can because we want to assist with the trash collecting process. And if it's too expensive, it will not be used. Below is some engineering standards we have selected. We are going to use the IP24, which deals with the environment the trash is placed in, the USB that deals with the GPS, the OSHA requirements for the human contact, the GPS so we can track trashy as well, and we also have a few technical product documentations that deal with the overall construction of trashy. And this will bring us into our approach.
So in order to design Trash-E concept, many iterations were made to imagine the overall mechanism. And using CATIA software, which is a CAD design software, we managed to create the concept in a 3D perspective. So the concept itself is the assembly of different design subparts, which will collaborate in the main mission of Trash-E, which is eventually collecting trash. So we have the swipper, plates, the bin, the rear cover, the supports, the track, and which will all be mounted into the chassis. Just one thing is that all these images are labeled with numbers. This represents the order in which they will be discussed later on in the slides. Now coming into brainstorming the main steps that Trash-E will follow to fulfill the main mission, which is collecting trash properly. So first, the robot will be recognizing the trash sample to collect, as you can see in the image. After that, which is step 2, is where the plate will be deployed and lowered to the ground level, as you can see visualized. And next, which is step 3, is when the swipper will initiate its rotation in order to drive the trash from the ground to the bin through the plate. And finally, which is step 4, is when the upper swipper will be raised so that the robot can resume its path and redo the cycle for other times.
So now for the chassis, we will be mainly using 3 materials. First of all, balsa wood that is characterized by its availability, durability, and low cost. However, balsa wood is not a strong material. That's why we are going to fix that using the glass fiber, which will add more strength and the elasticity needed in the chassis. We will glue this using the epoxy resin that will add more strength as well, and the water and heat resistance. How we are going to do this? Well, we are going to cut the balsa wood based on the dimensions defined in the design. We will take small portions of glass fiber of around 20 square centimeters and put them on the surface of the balsa wood. We will prepare our epoxy resin in a dedicated bottle, and we will glue this using a feather. All of this, and we will let it dry in a place where there is no sun exposure. All of this should follow a safety procedure by using latex gloves, face masks, and glasses, protection glasses.
From the locomotion side, whether to choose continuous tracks or wheels, we are basing our decision on the following criteria: suitability for heavy loads, load distribution, rough terrain navigation, traction, power efficiency, and maneuverability, and vehicle stability. From this table, we can deduce that the most perfect mechanism to opt for is continuous tracks. Next. We are proposing, in this case, DOI T300 to do the job of the continuous tracks with 1 driving wheel and 4 bearing wheels made from aluminum combined with a plastic rubber track made from engineering plastic. Next. To decide to find the torque needed for our robot, there are 3 main forces acting on any vehicle. The first one is the rolling force, which is correlated with the static friction coefficient. We have taken rubber against grass, since grass is considered a rough terrain to navigate on, with the value of 0.35, giving us 34.34 newtons. For the acceleration force, which is the force needed for a vehicle to reach from stationary position to a certain speed over an amount of time. We have taken 10 kilometers per hour since it is a reasonable speed to have in a crowded area, giving us 27.25 newtons. For the third force, we have it is the inclination, which depends on the inclination of the terrain. And we have taken, in this case, 15 degrees, giving us 25.39 newtons. Summing up all those forces will give us the resultant attractive force with the value of 86.98 newtons. Through it, we can deduce how many torque we will need per side of the robot, which is 1.2 Newton meters. For the battery life, it is expected to be 13 minutes in average, with a speed of 10 kilometers per hour in average. The maximum linear distance trash A can cover is 5 kilometers. This is deduced from the rule of thumb.
Next is the hardware overview for the electrical side. We're going to use a battery for our power supply, and this battery is going to feed two saber-tooth motors drivers. This will control two motors each for a total of 4 motors. The battery will also feed a DC to DC step-down converter, so we can safely distribute our voltage to our Raspberry Pi and Arduino. The Raspberry Pi will control the GPS, and the sensors will be split between both Arduino and Raspberry Pi.
So Ali just gave a really good description of the torque requirements for our DC motors that will drive our track system. And so we selected the Palulu gear motor, high power 12-volt motor to drive our tracks and move trashy around. We also have the 540 ADT motor listed above that we will actually use for the sweeper mechanism. Next, we had to select the motor drivers and we had to select the right motor drivers that would be able to handle the right amount of current for our DC motors. And so our DC motors, the stall current that the Palulu drew was 5.6 amps, and the stall current for the 540 ADT motor was 11.6 amps. And so we selected the Sabertooth 2x12 motor driver because the 2 means that it can drive 2 DC motors at one time, and the 12 means that it can handle up to 12 amps of continuous current. And so it fit our guidelines. It is a little bit costly, but it's necessary for the job that we need it to do.
So we wanted to come up with the battery. So we needed to know, like, what is our runtime going to be? And we were shooting for a goal of 30 minutes of runtime. So we took the battery that we selected, which I'll talk about next, and we used the average amp usage and the max amp usage to get a rough estimate of 2 times. So for the average amp usage of all our components, we're looking at roughly an hour and 13 minutes of runtime. And if every component was pulling the max amps, we're looking at roughly 46 minutes of runtime, which exceeds our goal of the 30 minutes. So the battery we selected was a Lapierre 22 amp hour battery. It has 14.8 volts, and it is very lightweight, which is a plus for us because we're trying to keep the weight of Trashy down as well. Next is our DC to DC converter. It has a plenty enough input voltage range for us to use, and it also gives us our desired output voltage, which is going to be between 3 to 9 volts for our Arduino. And the output current is high. We were going to use some other components, and we may go back and use them later on. This is why we selected this DC to DC converter. Also, the plus to this converter, it has a digital display, so we will not have to use a multimeter to check the voltage output as well.
Now, coming into explaining the mechanism of swipper end plates, which were discussed earlier. For the swipper end plate, they represent the critical components of the robots. So their design must match the tasks they are supposed to accomplish. So as far as the swipper is concerned, the ability to lift weights and shapes according to the technical design constraints is important. That is why their design was original and smooth. In addition, it should perform full rotation thanks to motors. On the other hand, the plate needs to have accurate angle rotations in order to reach the ground surface or be retracted in a fast and sufficient way. Lastly, for material selection, PLA material is the one matching all requirements we have, which are mechanical strength, availability, and cost. And all of this with a full mark.
So starting from the global vision we had of the sweeper mechanism, how it's gonna work and the limitations. We set first the ranges of the dimensions that we're gonna use and the list of materials that we can use. And these inputs, we calculated the inertial torque and then the total torque, which is basically the addition of the inertial one and the reactive moment the trash apply on the sweeper. These steps were organized in a code system. We had to go through them multiple times to get the optimal configuration. And then we selected the type of models we're gonna use. We chose a separate one for the plate since we need a high holding torque and low speed and a good control of speed. And we set a DC motor for the upper sweeper since we'll be needing full rotations and high torque and low speed. Then we selected the motors and we applied an RPM verification, which is basically just verifying the RPM if it gives enough momentum to the trash to travel to the bin. So the bin was designed to be detachable, and we set the dimensions in a way that it gives a respectable capacity. So we first set the width, and we set the width to be wider than the sweeper to accept any trash that comes from the sweeper. And then the length, and then the height. We couldn't invest more in the height since the trash may fall out. And then we selected the material resin as epoxy, because first it is malleable and it is robust, and we can manufacture it easily, and it is much more durable than metals, especially that it doesn't have a high reactivity to the environment like corrosion, etc., and it is low cost.
So on the side of sensors, this is a top-down view of Trashy. It is showing that the 4 sides of the robot will have a total of 8 sensors. There will be 2 on each side of the base. There will be 2 placed at the front, 2 placed at the back where you see the yellow circles. There will be 2 on each side where you see the yellow rectangles. This will create a sort of barrier for Trashy to recognize when it is going to run into something or something is within its perimeter. There is also a purple circle that you will see that will have another sensor, ultrasonic sensor, that we will put at the top. It will locate anything that is at the same height as Trashy that cannot be actually picked up. Also at the front, you will see another ultrasonic sensor that will be pointed down, that will have, it will be angled at about a 15-degree angle, so that Trashy will recognize when it is about to run off a steep cliff, for example. So in order to do this for object detection, we chose to use the HC-SR04 ultrasonic sensors. These are the main ones that I said will be placed on the sides and pointed down and at the top of Trashy. They have the least cost while also having a pretty astounding 4-meter range, giving it that bubble or perimeter around Trashy. Also, we need a temperature monitoring system to fulfill the design constraint. We have chosen to use this small LM34DZ temperature monitoring sensor. It has a cheap cost while also having a very good operating temperature, and it's only needed for the battery temperature monitoring purposes to recognize that if the battery overheats or the components, especially in the south, we need to recognize this for Trashy.
And with any autonomous vehicle, a major component is always tracking, because the autonomous vehicle needs to know where it is, and if you wish to track it, it needs to know where it is as well. And for that, we chose the Adafruit 4279 with its kind of robust nature. It's one of the top of the lines GPS that uses a standard deviation, which in the US that translates to a 1 to 3 meter accuracy at all times. And we chose this over other more expensive technologies because they would well, be more expensive, have more hardware, and out of our reach in this case. Next, we have our microcontrollers. In this case, due to our expansive sensor array we're going to be using, we're going to utilize both a Raspberry Pi and Arduino Uno. The Arduino Uno would deal with simple logic and sensor data interpretation, such as simple value recognition, such as if the battery was overheating and the temperature sensor read a high temp, it would stop the robot. And then the Raspberry Pi would deal with higher level communication with the user with its Bluetooth and wireless communication, as well as dealing with most of the navigation.
In our design, we use the rear cover as a covering that will allow us to protect our electrical components like battery and wires. It's also going to enable us to respond to the practical constraint that say that the robot's component must be IP24 resistant of water splashes and dusty conditions.
All right, for the software components, software is very important for chassis operation because it can deliver commands from user and notification from chassis without any problems. And we use Flask with Python language to develop our website, and then chassis can connect to the website using Raspberry Pi. For the user interface, we are considering a transition from a mobile application to a website. So a website is comparable to both personal computers and smartphones. And we have worked with students from the Mississippi State University College of Architecture, Art and Design to develop a friendly graphical user interface for our application.
Yes, so when we began thinking about a way to integrate Trashy into a website, we first began with our sketches, and here you can see where we began with the Trashy logo. We decided to keep it very simple, and for the color palette, we chose this simple four-color green because of one of the features that was really cool about Trashy is that it is energy emission. It's strictly electric. So you think green energy as well as like green like trash cans. And so we then begin to design icons, which are the essential part of navigating through the app. When you see the menu, you will see these icons that specifically represent the features and functions of Trashy.
After sketching out hierarchy graphs of our interface design, we came up with this simple wireframe incorporating our icon sketches into the pages for each web page. So to begin, you are opened up onto a login screen, and once logging in, you're sent to a home welcome page. And this is where you are able to choose the menu icon to click any icon to go to any page in the website. At the top right part of the screen, there is always going to be a battery percentage to show the battery percentage for your Trashy robot at all times. So for the first icon, you click the alert icon, and this sends you to the alerts page. This is where any trouble that your Trashy runs into will go, or any notification about it finishing its job will go here to let you know. For the second icon in the menu, it sends you to the Trashy status page. This is where you can see the percentage of life battery it has left, the capacity it has left in the bin, or the percentage of the area it's cleaned. And then our third icon for the page, it shows a map, and this is where you can flip through different maps depending on how many Trashies you have employed at the time. And this is where the user will circle this section and allow them to pick exactly where they want their Trashy to go clean.
Yep, so Trashy will send notification to user, including errors like low battery, bin is full or overheating, object collision, etc., or to alert that Trashy has completed the cleaning process. And also, the application also has a map that Amber has mentioned above that user can determine the cleaning area by drawing borders around that area. and then the GPS module in TrassE, we make sure that TrassE covered that whole area.
The fourth icon leads to the schedule page where you can schedule your dates, your times, and your location for the TrassE cleaning. The fifth icon leads to the user page, which contains all of your personal information that you entered when you signed up for the app. The sixth icon leads to the About page, which contains a little information about the creators of the TrassE. Finally, we have a short video on the TrassE app transitions.
Oh, now it's not going to work inside. I don't know why. It's a 30-second video that shows the ins and out transitions of the app itself. I wish I could show it to you, but for time purposes.
Yeah, that's okay, Randy.
Okay, for the embedded system architecture design, we have three main stages of TrassE during operation. In the first stage, after turning on, TrassE will receive information and commands from user via the application. And during the second stage, TrassE will start the cleaning process by going around the cleaning area, detecting objects and obstacles by sensor, and cleaning the trash by sweeper and plate. In the third stage, whenever TrassE finishes its cleaning process or approaching the errors that I have mentioned above, TrassE will notify user via the application and will turn off after a while if it receives no responses from user to save energy. TrassE can also be forced stop if user want to stop it at some special cases. That's an operation of TrassE.
So far for our entire team, we had our first team meeting, both for ECE and EME teams, as well as together, and we have weekly meetings that we have, even including the time difference. We had to research our project and come up with a design, which we have done, as you can see. We have ordered parts on both sides, and we have started to actually construct subsystems. As you can see on the right side of the screen, we have started to mimic the design of the mechanical engineering's CAD design. And we have not yet begun testing because we have not gotten a few parts in yet, and we have not given our later. So overall, laborers even may minimize the use of them. It works longer without breaks. It allows full interaction during the cleaning process via the mobile application or website, and is used to make the earth a cleaner, greener place. Thank you for your time, and we will open for questions.
I saw that we got a link to the video. I'm gonna try to show that quickly and see if we can get that to go. Let's see. Let me start it here. So here's just that quick video that y'all wanted to put together. Hopefully it's showing up for everyone. All right. Well, again, team, that was a true pleasure. I'm really impressed that the coordination across international boundaries and department boundaries. I thought it was a very strong presentation, and I enjoyed it. I particularly liked, so the UI is just gorgeous. I'm really excited about what the CAD team has done. I think the mechanical and electrical pieces look great. I just can't wait to see this thing run. Let me try to stop that share there.
I agree, guys. So we don't have a whole lot of time for Q&A, but I'm really impressed how all these teams have come together. And I really love the fine arts component of the team because I just think it helps the ECE students maybe understand just the value of the fine arts. It's such a valuable component, I think, of this this blended team.
Yeah, I agree. I really enjoyed this presentation. I was really good at it.
Thank y'all.
I'm really glad that we could bring that video up. I was going to offer to show it at the end, but I wanted to show everything working.
It does look really good.
I do have a quick question though concerning the app.
Okay.
So, like the implementation of like the embedded component, the sensors, and then trying to do like an app backend and also an app front end. That's like a massive software undertaking, and I don't think it was at least clear for me like what part of the team is responsible for implementing the front end and back end sides of the app.
If you'd like me to answer that, Brittany, I think I kind of can explain. Well, the front and back end, the far front end, we have Qual working mostly with the ARC team on the kind of website, and the back end is going to be done in kind of a combination stage between me, Qual, and some of Randy, because it's all kind of jumbled together, so to speak. Most of that is going to be done on the Raspberry Pi. Good hunk of it is going to be done between me and Qual, with the direct interaction between the Raspberry Pi processing data and giving feedback back to the users. If that kind of makes sense. And we are going to stick to fundamental commands and other things. The big thing that's going to change is it's not going to be a live update to the app. It's going to be more of a static transmit and receive environment. The user's going to send some command, and then the robot will act autonomously, interpret that command, and then send the user feedback saying yes, no, got it. If that answers your question.
It does, yeah.
So, for the back end of that website, we're going to use a Flask program provided by Dr. Brian Jones. We use Python language to build that website and store at the database as well. So, if that answers your question.
It does.
Yeah. I'm sorry, Ron. We have got to wrap it up, guys, so we can move to our next presentation. Thank y'all so much.
Yep, great presentation, excellent job. Kobe, paying attention, there's a way that Wrist Motion Monitor, I think, took Flutter and can export XD to Flutter and use the art directly from the art team, and something you might be able to take advantage of.
I gotcha. I will take a look at it to see. Thank you so much, Jones.
Yep, see y'all in the next meeting. Well done, everybody.
Thank you so much.
Thank you, sir.
Thank you.
Good job, guys.